Hello, welcome to the 34th class in this course, the physics of materials. In the last class we went through a detailed calculation, a series of equations which you saw in the form of slides, wherein we tried to look at what would happen to the wave vectors of the and the energy values that the nearly free electrons have as a result of their interaction with the periodic potential of the crystal lattice. So we did this with a series of equations that you saw, and as I mentioned, it is something that you can yourselves do as an exercise. However, you have them in the form of those slides where you can refer to them and see for yourself if your procedures are correct. At the end of it, we found that we had an equation where we had on one side the cos of some angle and on the other side an expression. And what I indicated to you at that stage is that if you evaluate the expression, you can find that it will have a series of values which do not have to stay within the plus or minus 1 boundary. Okay, so as long as those expressions stay within the plus or minus 1 boundary, the energy values corresponding to those expressions are allowed energy values. In fact, the only thing you will be changing in those expressions is the energy, because everything else will be fixed by the system. And so as you change the energy, you will find that for some values of energy the expression will evaluate to between plus or minus 1, and so then that equation makes sense, because you have cos of some angle which has to evaluate between plus or minus 1 and an expression which is also evaluating to plus or minus 1. So those are all energy values that are now allowed for the system. At specific sets of energy values, you will find that the expression evaluates to quantities which are more than this window. So they are either greater than plus 1 or less than minus 1, and those values then are not allowed for the system, I mean they do not make sense for the equation, because you have something on one side of the equation which requires you to stay within the plus or minus 1 window. Okay, and the interpretation, as I said, is that then those energy values are not allowed for the system. So that is how we see that we can use the Schrodinger wave equation and look at the behavior of electrons in a structure that has a periodic potential window, potential wells, and in that process, by using the Schrodinger wave equation on the electrons, both under conditions where the potential is 0 and the potential is V naught, we are able to then look at two situations, and we said that those equations have to be reasonable. Therefore, at the boundaries, the values from either side, whether you are coming from the potential equal to 0 or potential equal to V naught, the values should become equal, and also the slope should be equal. So it is on this basis that we created all those equations and solved them. Okay, so so you have now become familiar with the procedure for such a process, and you have also become familiar with how you would interpret this work. And of course, this is all work that was done a long time ago. We are going over it to understand, for our own understanding, to see how such a process is done and what we can interpret from it. So we finished off by realizing that we now have both, based on our last two classes, a pictorial way to understand approach which gave us the band structure. And we also did we did the calculations using the wave equation, the Schrodinger wave equation, and that gave us also the band structure, the band gaps at least. Okay, and I also pointed out to you that we have actually done this in a much more detailed way than you have perhaps ever used, you have been exposed to before, and in principle we had one diagram. The utility of it you have not yet actually completely seen. We will do that, we will understand the utility of it a little later, maybe in the next class. In fact, we will look at it. So this was E, this was K, and we have the guideline which is the free electron parabola, and we said that at the Brillouin zone boundaries, pi by a minus pi by a minus 2 pi by a and 2 pi by a. At all these boundaries, this nearly free electron parabola, which itself is a set of discrete points, this near free electron parabola is distorted, and specifically we drew the distorted structure as something like this. Okay. This is something like that. So if you draw it to scale, this is how you will see. Basically they all have, they will all finish up at the same values if you are looking at the same direction, and this then becomes the band. Okay, so this is a band, and this lower end is also a band. So I am just going to draw two bands here for the moment, and that will illustrate our purpose. So we have a representation for the band structure in the E versus K space, which has some detail here. The utility of this detail we have not really examined, and we will hold that off for one more class. Next class you will see the utility of this detail, which is what value of energy is permitted at which value of K. So this is E versus K diagram. We have actually also the same information or an aspect of the same information being represented to us here in the form of a flat band diagram. So here also we have, so similarly you can have other bands. I have just drawn two bands here, obviously you can have bands above it, so to speak, and so we just have, you know, energy levels here, a series of energy levels here, and a series of energy levels here, and exactly and these are all based on what is allowed in the system. Okay, I have throughout this course at various points I have pointed out that there is something, there is this concept of what is allowed in the system, and there is also this concept of what is actually being used in the system. Okay, so those are two separate things. So that is why we have the density of allowed states and the density of occupied states. So the of those that are allowed, some up to some level is occupied, right. So this is all allowed in the system, these are all allowed values in the system based on where the Fermi energy is, which is the highest value of electron energy in the system, which let us say arbitrarily I am setting here. If I set this as EF, then up to here everything is occupied, all these energy values are occupied. So all these discrete energy values are occupied up to this Fermi energy EF. Above this you have vacant space, alright. So even with respect to the today we will focus little more on this flat band structure, then we will come back to this structure here in the next class. In the flat band structure we can see that, you know, you can identify the allowed energy values, and you can also identify the level up to which those energy values are being used. So on just this basis we can of course say something about the system, and what we conventionally say is that, you know, we can have if you look at the last two bands as you go up in energy, some two bands whichever are the highest energy level bands. So then we have the following situation, we have something in the middle which is the band gap. These are the energy values that are not allowed. This is typically if it is the last occupied band, fully occupied band, this is called the valence band. So this would be the valence band, and this empty band here would be the conduction band. So between based on the layout of all these bands and what is being filled up, we have materials with different properties. Okay, so for example if you have this structure here where you have an empty conduction band and a filled valence band, then you either have an insulator or a semiconductor. So it is either an insulator or it is a semiconductor. If you have a structure that looks something like this, whether or not it is actually an insulator or a semiconductor simply depends on the extent of this band gap. Okay, so if you have this band gap is typically denoted with E subscript G. So this is what we have there. So if you have Eg greater than 2 electron volts, okay, if the band gap is greater than 2 electron volts, then it is an insulator. If on the other hand these are all filled states, if we have Eg less than 2 electron volts, this is called a semiconductor. Okay, so greater than 2 electron volts is an insulator, less than 2 electron volts is a semiconductor. So in that sense, what you see for semiconductor and insulator, at least in concept, is the same. It's a matter of the value that you see here, and in principle the reason they are what they are called, the names that they are given is based on the fact that if you have a band gap greater than this band gap represents effectively the amount of energy you have to provide to get electrons off of this valence band into the conduction band, and so therefore the larger the band gap, more is the energy that you have to provide for this transition to occur, and only after that you are going to see any kind of conductivity. And in general, if it crosses this threshold, for the purposes that we typically use materials for, this tends to be very insulating, and if this is the kind of value involved, less than 2 electron volts, then the properties that it shows you falls more in line with what we are utilizing and calling as semiconductors. So that is how this nomenclature comes, right. So this is what is there for these two. For metallic systems, we have actually a couple of two different possibilities that can occur if it is a metal. We can have one situation where your the last filled band is actually half filled. Okay. So here also in a sense there is a band gap here, but it is not the band gap that if you want to call this, we can call this a band gap, but it is not the band gap between what we would call the in the sense of a valence band versus a conduction band. So it is not a band gap in that sense. Further down there are gaps, I mean further down in energy there are gaps, but we are more interested, as I always mentioned, at what is happening at the Fermi energy level. So this is the Fermi energy level, EF is the Fermi energy level. Okay. So if this is the Fermi energy level, it is the last occupied energy level for the electrons at 0 Kelvin. This is the Fermi energy level. We are interested in what is going to happen here. That is what often dictates what is the property of the material. So if you look at that, for, as I mentioned, for electrons to move through the system, the ease of movement depends on how easily they can locate energy levels immediately above them. Okay. So here there are energy values immediately above the Fermi energy, which are all vacant. So if you give it slight amount of energy, the electron can get onto those energy levels and then it is free to run around. Okay. So that is how conduction occurs, and therefore this is the this becomes metallic. Metallic simply conveys the sense that, you know, amongst its various properties is the fact that it conducts electricity very well, and also as I mentioned, one of the defining characteristics is of course the coefficient of thermal coefficient of resistivity, which is negative. So you raise the temperature, the I am sorry, is positive. So as you raise the temperature, the resistance goes up. So that is what we see in this system. Okay. So for resistance, the other way in which metals could also have their band structure is if they have overlapping bands. I will just displace the bands so that you can see them clearly. So these are all filled levels, and this is a vacant band. Only thing is that the bottom most energy of that vacant band is less than the topmost energy of the filled band. Therefore electrons are able to easily get onto the other band and keep moving around. So therefore this kind of a structure where there is overlapping bands also enables that material to be to show you metallic behavior, okay, which is very good conduction with very little amount of energy. So this is the general layout of how these materials are. Incidentally, I will also point out one other concept here. The Fermi energy for metallic systems has been defined the way we have seen it, and we have discussed this in considerable detail. However, there is a difference when you talk of semiconductors or insulators. So I just briefly show you in this schematic that we have shown. By convention, for insulator or semiconducting materials, this kind of a material where you have a filled band and then a band gap and then a vacant band, when you have this kind of a situation, by convention halfway between the bands is where EF is. By convention, that is what the Fermi energy is. Okay, so halfway between the bands is what the Fermi energy is. So this is one case where the Fermi energy is actually at a location where there is a band gap. So in fact, when you say this is the Fermi energy, an electron can actually not sit at that energy. It is actually, it's a forbidden energy for the system, but by convention that is what is chosen as the Fermi energy for semiconducting systems. And also the Fermi energy, of course, as I mentioned, conveys to you what can or cannot be done in the system. So therefore, when you dope, these are all the intrinsic semiconductors, we will see that in our next class, but basically when you dope this system, the Fermi energy effectively you are raising or lowering the Fermi energy of the system. So that is effectively what you are doing. Okay, so this is the way in which it occurs. So we now see that there are a lot of different properties of materials that we can associate with the bands, and we have seen in the last few classes how bands arise. It is now of interest to look at a couple of things. We have tended to approach this problem, this entire problem of the band structure of materials from a certain perspective, and that perspective was that we had this set of atomic cores and this cloud of so called free electrons running across the material. So this is what we did. Our approach, the way we have done it, is in fact called the free electron approximation. So everything that we have done so far, effectively all the theory that we have developed so far represents this general approach referred to as the free electron approximation. Okay. So the free electron approximation starts off with the position that you have free electrons in the system, and then gradually introduces all the details of the system, especially the periodic potential of the system into the picture. So that is how you get the free electron approximation. Now effectively the same result can be obtained if you actually start at the other end of the picture, which is the opposite of the free electron approximation, wherein you are actually starting from a condition that the electrons are bound. Let me just explain here a little bit in greater detail. Here we have already said that we have created a solid. Okay, so in this free electron approximation we already have a solid to start with. So all the atoms are already in position. They have already released that 1 electron or 2 electrons or 1.5 electrons on average per atom, whatever it is that they are doing. They have already released that into that free electron gas. That system at that stage is where we are analyzing the system. Okay, we take it at that moment where you already have the solid, and we do our analysis on the basis of what currently exists in that solid. The opposite approach is one where you do not actually have the solid to begin with. Okay, so you say that you have actually only independent atoms to begin with. You bring the atoms together, and in the process of bringing the atoms together you build the solid. Okay, so when you build the solid, whatever is happening, that is how you try to understand how the property of the solid has come about. You sort of know what the properties of each of the individual atoms are, and then you bring those atoms together, create the solid, and then try and understand what is the why is the solid showing you a certain property. Okay, so in that case the electrons in that situation are originally all belonging to specific individual atoms. In other words, they are bound to those atoms. Okay, so that approach, which is the opposite of this free electron approximation, starts from its starting position is that you have an individual atom, though that individual atom has electrons at specific energy levels, and those are specific discrete energy levels, and those electrons are bound exclusively to that atom. You take such atoms and those electrons associated with each of those atoms, bring them together and create the solid. So the starting point there is that the electrons are bound tightly to each of those individual atoms, and therefore it is called the tight binding approximation. Okay, so you start from the individual atoms where the electrons are tightly bound. The names can be slightly confusing because when you say tight binding approximation, you are actually starting with atoms that are not tightly bound, they are free atoms, the point is the electrons are tightly bound, that is the difference. Okay. So in this case the starting position is that the atoms are free, but the electrons are tightly bound to each of those atoms, that is why we call it tight binding approximation. In this case of course the electron itself shows up in the name, therefore it is very clear it is a free electron approximation. However, you will note that here the atoms are tightly bound in the sense that they are stuck to those lattice sites. Okay. So for the atoms the situation is the opposite as it is for the electrons with respect to the electrons. Here the electrons are free, the atoms are stuck, here the atoms are free, the electrons are stuck, that is the starting position. Okay. So and that is how you build the solid. So we will briefly look at what this tight binding approximation says. So what it basically says is that if you take a given atom, you have electrons at specific energy levels. Okay. So you have electrons at specific energy levels associated with this atom. Now if you take a solid, you have a huge number of these atoms, alright. So basically these are all atoms that were let us assume that they are all atoms of the same kind, that you are not really changing the type of atom that we are looking at here. Therefore if you take the same atom, if you take a million such atoms, or each one of those million atoms will have exactly the same energy levels for the electrons when they are separate. Okay. When you have separately you have laid out all those atoms, the energy levels of those atoms will be exactly the same. So that is how, in fact that is the characteristic of the atom, that is how we know that it is that atom, it shows you all those properties, right. So that is how these values are. Now as you start bringing them together, okay, so we also have some kind of a sense of the inner shell electrons are closer to the core of the atom, the outer shell electrons are a little further away from the core of the atom and so on. So when you bring the individual atoms which are initially separated, you start bringing them together, then the as you get them closer and closer and closer, the electrons at the outer shells begin to overlap, the electron clouds begin to overlap. If we based on the description we tend to use, electron clouds overlap, so the outer shell electrons begin to overlap, and then if you push them even further closer, then slowly shells which are below the outer shell also begin to overlap. So this kind of a system occurs. However, regardless of whether you start from independent atoms and bring them together, or you start with a solid where the electrons are already running around in the solid, regardless of these two, given the nature of electrons, we are forced to accept the fact that they are subject to the Pauli's exclusion principle. In the free electron approximation, we implemented the Pauli's exclusion principle using the Fermi-Dirac statistics. Here what we are basically saying that is that as the energy levels in the tight binding approximation, as the atoms get closer and closer and closer, when a given energy level of and therefore the shell of electrons begins to overlap, they are forced to split in energy. In other words, what was originally a single energy level, right, a single energy level will now split into enough number of energy levels above and below this original energy level, such that it can still accommodate all the electrons. For example, let us say I take 100 atoms, okay, we have 100 atoms and I start moving them closer and closer and closer together. What will happen is as they begin to overlap, as the outer shell electrons begin to overlap, this energy value here, whatever is this, I will just call it E1, E2, E3. Let us say we have brought the atoms close enough that only the E3 energy value and therefore that corresponding shell of electrons are beginning to overlap. That E3 energy value will now split into 100 different energy values. Let us assume that for the moment it is a single state, it maybe has 2 electrons per state, whatever, we will assume it is a single state there, and it will now split into 100 states. Because you have brought 100 atoms together, there are 100 electrons that need to be accommodated. All of those original 100 electrons were at E3. Now they will split up here and slowly split into a wide range of energy values as they get closer and closer and closer, so that they can still accommodate all of those 100 electrons. Okay, so or if you are assuming 1 electron per state or whatever. So therefore this what is originally one state will now become 100 states. Okay, 100 energy levels it will become. Around this value it will become a set of energy values around that energy value. So this process is then called this tight binding approximation. We will just draw this, we will draw the energy versus as a function of, so clearly it really depends on how close you bring the atoms. If you take another atom here and the same energy values here, So what we actually see occurring will depend on the exact interatomic separation. Okay, so as you bring the interatomic separation closer and closer, you will see the appropriate kind of splitting. That is what the tight binding approximation describes. Okay, so we will just pictorially at least look at it at the tight binding approximation and see what we can expect. So we will make a plot now of interatomic distance, interatomic separation. So this is the average interatomic separation spread across all of those atoms. If we are looking at 100 atoms, that kind of that's what we are looking at, and energy. Okay, so let us say initially the atoms are very far away, very far from each other. Okay, so when they are very far from each other, they are not really interacting with each other. So every atom has the energy levels corresponding to the original energy levels of that atom. Okay, so whatever is the energy levels of that individual atom, that is the energy level that they have when you keep them widely separated. So that at that point they are not really interacting with each other. So we will just say that the same E1, E2, E3, I just put something there. So we will just assume the same thing, E1, E2, E3, E1, E2 and E3. Okay. So as you bring them closer, what you will see is I will just draw it here, then I will describe it. As you bring them closer, at some point the outermost shell electrons begin to the clouds begin to overlap, and at that point the energy levels are forced to split to accommodate all those electrons within in an energy value with energy values very close to that original energy value that they had, but it cannot keep them at the same energy value because that would then violate the Pauli's exclusion principle. So therefore this begins to split. So I will just draw it here like this. Okay, so it splits like this. You actually have a huge number of energy values here. Exactly how many energy values you have here will depend on the number of atoms that you are pulling together. So because that many electrons have to be accommodated, so that is how you will get this. If you so this is what is happening to the outermost shell. If you take the next shell of electrons, which is the next lower energy, they do not overlap at this point. Okay, so at this point only the outermost shell electrons have overlapped. You have to bring the atoms much closer before the next shell of electrons begin to overlap. Okay, so but then the general trend of the behavior will look similar. You bring it much closer, and you will start seeing a similar kind of behavior. So you see a behavior that looks like that. Again, that consists of a series of energy values. So you see something like this, right? And for the the lowest energy value that we are looking at, the same concept will hold true. You have to go to even much deeper, you have to bring the atoms much closer before they begin to overlap, and so you start seeing a behavior that looks like that. So this is what we can expect if you take a set of atoms and you start moving them together, and we have now drawn what we can expect from this situation based on all possible interatomic separations that we can think of, which we can perhaps experimentally create or enforce on the system, right? Now what is it that we actually have in the system? So this is the general picture of what is possible, right? What is possible is this is the general system. Now we could have different interatomic separations. Okay, so we can create a solid with a certain interatomic separation, we may be able to create a solid with a different interatomic separation, we may be able to manipulate the interatomic separation. Okay, so these are all things that we have at our disposal. So what we see is the band structure of the material, the band structure that eventually exists in a material that we probe, that we are able to experience in the form of the property of the material. That band structure depends on whatever is the equilibrium spacing of the atoms in that material. So whatever happens to be the equilibrium spacing, so let us assume that one possible equilibrium spacing is here. Okay, so corresponding to that we can draw a line, vertical line. So if I just call this x1, so when equilibrium spacing is x1, we will see we will basically see, so I just draw it here at x1, okay, we can draw it this side maybe, so it will be clearer to see. So at x1 this is E, we will see a single energy value corresponding to this E1, we will also see a single energy value corresponding to E2, and we will see this band, here. So this is now how the flat band structure will evolve in when you use the tight binding approximation. In this picture comes from the tight binding approximation, and when you bring this picture together with the actual interatomic separation that exists in the material, you can understand how its band structure will evolve. So at this interatomic separation, this energy level remains undisturbed at the original energy level, this energy level remains undisturbed at the original energy level, this energy level has split into a band which is this width, okay, because that corresponds to this x, and that width if you just draw here you get this. So you have a flat band structure flat band representation of the band structure in a material where you see this tight binding approximation of this form. This picture actually is much more gives us further insight, because you can consider changing the interatomic spacing, you can change the interatomic spacing. So for example, I will say that we now have a new interatomic spacing which is here, so this is x2. So what do we have at x2? We can again draw the line vertically up here, okay, so we have x2. At x2 we will draw the band structure. At x2 this energy value here is undisturbed, E1 remains undisturbed, so it remains a single energy value as before, so that is what we have. At x2 even this energy level E2 has split into a band, which is a relatively narrow band here, so that is the band that we have here. So if you look at the band here, it is roughly something like this. So that is what roughly it is going to be, that one and that one. So that is the band, so that is already a band that is split, right, and the band that is above it has actually become wider. Okay, so based on the interatomic spacing we have different band structure now that this material can have, right. So we have a material which based on the interatomic spacing, simply based on the atoms you can come up with this diagram, regardless of the actual interatomic spacing you can come up with this diagram, and you can select a particular interatomic spacing and you can see what will be its band structure given that interatomic spacing. Okay, so when it forms a certain crystal, some kind of a crystal structure it forms, based on the interatomic spacing you can now predict, you can understand how its band structure would have come about. So you can see how one band would show up and another band would show up in this material, and so that is how the structure would show up. And of course we are assuming now these are all only the available states, right, these are all available states, we have not indicated how much is filled and what is filled. Supposing for instance there is another band on top which is filled, or which is, let us say, which is empty, okay, so we could have thought of another energy level E4 and that would have given a set of that would have overlapped even faster, you would have had a set of empty energy levels here, and then based on the separation between that band and this band, and similarly the same band there and this band here, so clearly the separations are going to be different, it is going to be closer here, it is going to be further apart here, okay, so this gap is going to be larger here, it is going to be smaller here. Based on the separation we could either have this material being insulator or being a semiconductor, okay. So therefore we see that as a function of interatomic separation we can use this tight binding approximation and we can understand what might be happening in the material, how it could be changing its property. In fact people essentially use this idea, you can actually change a semiconductor's semiconducting behavior, because in semiconductors manipulating the band gap is a very important thing, and so this is a tool that you have available to you to manipulate the band gap if you should choose to do so. So this is one way in which you can do it. Okay. Now the same idea we can actually look at in a slightly different angle. Okay, so we are talking of interatomic separation here, right. So we can look at interatomic separation also as a function of pressure, for example. So that is, see, when you strain a material, when you stretch a material, you are raising the interatomic separation. So when you pull a material, you are as long as you are doing it elastically, okay, elastically you are doing it, you are marginally increasing the interatomic separation. Once you start plastically deforming it, that is different, that is a different situation, then entire sets of atoms are moving, but as long as you are doing it elastically, then you are marginally changing the interatomic separation. When you put you are raising the interatomic separation when you stretch the material. When you put pressure on the material, you are actually compressing the material, which means you are trying to force the atoms to take a smaller space, therefore you are reducing the interatomic separation. So we will just see what would happen if you put you increase the pressure that a material experiences as you put I mean subject it to high pressures. So we will again look at energy, and this is pressure, this is energy here. Okay, so we will just say that this is a conduction band energy value. Okay, so some energy value, I will just draw it and then I will explain it to you. So let us say this is the conduction band, it has a certain energy band at some pressure, let us say this is atmospheric pressure, I will just say this is at 1 atmosphere. So at 1 atmosphere pressure, so you form this material at room temperature and atmospheric pressure, let us say we do that. Under those conditions it has a certain band structure. So we can say that the valence band has this is the set of range of energy values over which the valence band exists, that is the range of values over which the conduction band exists, and halfway between them somewhere here is the Fermi energy EF. Okay. Now as you raise the pressure, you are forcing the atoms to come closer and closer. So if you look at our picture here, if you come back to this picture here, as you force this atoms to get closer and closer and closer, the bands widen, right, the bands begin to widen, you get wider and wider bands. And this is true for any band that you are looking at, any band structure that any band that you are looking at, it is essentially widening. So if you come back here, we will say that this is the conduction band and this is the range of energy values over which it exists at atmospheric pressure. As you raise the pressure, slowly the conduction band begins to widen. Okay, so this widens very significantly. Then similarly valence band, you can assume that originally at 1 atmosphere this was the width of that band, and as you raise the pressure, as you bring the atoms closer and closer, the valence band begins to expand in energy values. So what is actually happening is that, see this value here, so you now have the conduction band and the valence band, the difference in energy between the highest energy of the valence band and the lowest energy of the conduction band, that is your band gap. So this is here is the band gap. Okay, so we have a band gap here. So on this picture we see that as you change the pressure, as you raise the pressure, you are changing the band gap. The band gap is actually whatever is the initial value, it is steadily decreasing. Okay, the band gap is decreasing as you raise the pressure. So what will happen is, so we will assume that this is the Fermi energy. Our original definition still holds. If it is if Eg is greater than 2 electron volts, it is an insulator, and if Eg is less than 2 electron volts, it is a semiconductor. Right. So assuming, like, we start with something that was an insulating material, so what we will see is up to some point, let us say that here the Eg becomes 2 electron volts. Okay, so that is an arbitrary designation. Let me just say that this is 2 electron volts. Okay, so that is 2 electron volts. So we can now consider three situations. okay. For pressure up to here, as you raise the pressure of this material, as you raise the pressure that this material is subject to, up to this point this material behaves like an insulator. The same material, as you raise the pressure further and further and further, the band gap of the material now has decreased to less than 2 electron volts. So the material now begins to behave like a semiconductor. Okay. If you now go in pressure past this point also, if you have raised the pressure past this point here, so this is P1, P2. So when you go past P2 in pressure, what you see is that the bands now begin to overlap. The valence band now begins to overlap with the conduction band. Therefore, at pressures past this point, the material now begins to display behave like a metal. Okay. So we now see, so this is Eg is greater than 2 electron volts, it is an insulator at for P less than P1. Eg is less than 2 electron volts, it becomes a semiconductor. So that is pressures between P1 and P2, and overlapping bands. It implies it has become a metal, that is for P greater than P2. So when you go in pressure past P2, the same material, exact same material, the atoms are all exactly the same, and we can assume even the crystal structure we have not really, at least the symmetry we have not changed, we have changed the dimensions of the cell, but we have not changed the symmetry. So as you simply raise the pressure in the system, everything else being the same, the material moves from being an insulator to being a semiconductor to being a metal. Okay. So what I wish to convey to you is that there is a lot of interesting information here. It means first of all that when we test materials, we have to always keep in mind that we are testing materials at often we are testing materials at room temperature and atmospheric pressure. Okay. So that is often the case. We can always test them under special conditions, there is no doubt about it, but sometimes we forget the fact that we are conducting a test at room temperature and atmospheric pressure, we are taking it for granted. Often the end use of the material may be under conditions where the temperature and pressure are very different from room temperature and atmospheric pressure. Therefore, at that point many things about that material might change. Okay. Some of the properties we are more what shall I say, sensitive to, we are more aware that based on our understanding of things. Certainly, for example, temperature effects we take into account often. We often know that as you raise the temperature, materials soften, materials melt, materials can boil, so a lot of things can occur. So this is something that we are more intuitively aware of because we tend to see it more often in day to day life. Pressure on the other hand is something that we do not experience a lot in terms of change. 1 atmospheric pressure is something that we assume. Changing pressure is not something that is often convenient in an experimental sense, especially when you are dealing with metallic systems and such. So that is something that we tend to ignore. But on the other hand, if you were to send spacecraft into space, you are now going from 1 atmospheric pressure to something that is virtually 0 atmosphere to vacuum basically. Okay. So to vacuum you are sending it, you send it to some other planet, you send it to some other planet which has whatever atmosphere, it may not be a breathable atmosphere, it may consist of methane. Okay. But the important thing is the pressure might be different. Okay. So the pressure experienced by your components might be different. So in addition to any other chemical reaction that might occur in that atmosphere, the fact is that even if you had insulated everything, you will find that the pressure being experienced by a component, if you have not accommodated for if you have not sealed it so that pressure is not experienced in the system, if you have not made it pressure tight so to speak, then pressure experienced by the systems can be different. If you go to other planets where the pressure is very high, then these things can change, material properties can change. So and therefore something that you may have made a circuit assuming something is going to be a semiconductor. If you send it to some location where the pressure is very high, it may actually become metallic, and therefore your circuit might fail. So it is something that you have to be more aware of. You have to be aware of the fact that the property can change very dramatically even as a result of pressure. Okay. That said, I also want to point out that the in general the sensitivity to pressure is rather poor, okay. Even though this picture shows you what can happen with pressure, what is not really conveyed to you is, given that this is 1 atmosphere, what is P1 and what is P2, okay. So the actual values are not really indicated here. So for example, just to give you an example so that you understand the scale of what we are looking at, hydrogen, which we think of traditionally as a gas, okay. So it is only something that we are conventionally used to thinking of it as a gas, maybe to some degree as liquid hydrogen if you can liquefy it and for storage purposes, but this is conventionally all that we are looking at. But if you actually put enough pressure on it, it can become a solid, okay. And if you keep raising the pressure on this hydrogen solid, you can reach a pressure at which point the bands, I mean you create a situation where hydrogen becomes metallic. So this is possible, okay. So or at least theoretically predicted, expected that it can happen. So this is a possibility, but the kind of pressure that you are talking of is in the millions of bars. So okay, it is of the order of a megabar. So a bar is 1 atmospheric pressure, so this is 1 bar here. So if you are talking of a megabar, you are talking of a million atmospheres, okay. So that is not something that you are going to generate that easily, okay. So it is not something that, so that is what I mean by saying the sensitivity to pressure is rather low. Many many materials are much more sensitive to temperature, many material properties are much more sensitive to temperature than they are to pressure typically, okay. So as a result, and certainly this is true with solid systems, okay. For gases that is different. For solid systems, when you take a solid system and you analyze it, typically you will find that its sensitivity to temperature, the sensitivity of its properties to temperature is much higher than its the sensitivity of its properties to pressure, okay. So therefore, but at the same time I think it is worth notice keeping in mind that properties can change with pressure, okay. So and that is what is being conveyed here. In particular, the electronic properties are being shown here, and so you understand that you can go from an insulator to a semiconductor to a metal simply by changing the pressure being experienced by a component, okay. So this is what we have. So what we have looked at today is we have kept in mind the fact that much of the discussion we have done so far has been based on the free electron approximation, and which basically has started with the assumption that you already have free electrons in the system. So the electrons are already there, you are only explaining what the behavior of those electrons is. The electrons are already there in that atmosphere, and so we are looking at those free electrons, we are looking at what is the impact of, first we ignore the impact of the periodic potential in the lattice, and later we introduce the periodic potential of the lattice into the system, and then we understand the properties. Today what we have looked at is the fact that if you take separate atoms and you understand the description of the separate atoms independently, and you move those atoms together, in that process also you can try and understand, you can try and predict what are the properties of that solid going to be when you start from independent atoms and push them together, okay. So in this process also you can create the same kind of understanding of the material, and that is called a tight binding approximation. Now in principle, in terms of predictions, both these properties, both these approaches, whether you are talking of a free electron approximation or a tight binding approximation, in principle given that they are all essentially trying to explain the same things to you, at the end of the day if you take a given material, both these approaches should actually give you a reasonably good prediction of the property of the material, okay. So that is one thing to be said about both the approaches. However, given the fact that a metal actually has this general structure, that you have this ionic core and this free electron gas, that picture fits a metal pretty well. Given this situation, what we find is the free electron approximation is much more relevant. If you look at this free electron approximation, I mean this free electron approximation is much more relevant, much more likely to give you a good prediction for metallic systems, okay, simply because the situation it is examining or its starting point is very close to what a metal is already. So that is a good starting point for a metal. So therefore the free electron approximation is generally what is looked at in greater detail when you talk of metallic systems, which is a very large part of your periodic table, and that is why we have spent so much of time on the free electron approximation. Generally for semiconductors and insulators, the tight binding approximation it tends to give you is at least considered more likely to give you the right kind of analysis in an easier sense. So for semiconductors and insulators we this is a perhaps a slightly better approach, or a more appropriate approach is the way I would say it. The more appropriate approach is tight binding approximation. For metallic systems, free electron approximation is the better approach. So this is how these systems these approaches compare with each other. I will just conclude by just pointing out one more aspect that we have not really touched upon, which is the fact that regardless of this which approach you are taking, we have already seen now that the band structure, if you are talking of free electron approximation, we have seen that there are Brillouin zones and such, and then the band structure evolves based on the interaction of k vectors with the Brillouin zones. The important thing to note is that the location of the Brillouin zones is at different places based on the direction in which you are looking at. Okay, so we already saw that you have some polygonal shape of some sort which appears based on what system you are looking at. So the Brillouin zone appears zones can appear at different distances from the origin based on the direction in which you are looking at the material. Therefore the k vector and its interaction with the Brillouin zone can occur at different locations. Okay, which simply means that based on the direction in which you are looking at in the material, the property can change, because based on the direction you are looking at, the definition of which is the allowed energy level, which is the next allowed energy level, is there an overlap, is there no overlap, all those things are changing based on the direction in which you are looking at in the lattice, because the Brillouin zone appears at various locations at different positions within the structure, right. Similarly in the tight binding approximation, it only talks of interatomic spacing, it is not telling you in which direction. So depending on the direction you go, again you can start seeing variation in properties. So therefore both these approaches can also predict to you, can also convey to you the fact that anisotropy can exist in a material. Okay, so what we had in our earlier models, we were unable to show you anisotropy because we assumed a uniform number of free electrons per unit volume. These approaches can actually show you the anisotropy. Certainly the free electron approach, when you take into account the fact that the Brillouin zone is at a different position based on the structure at various locations, it can be at different positions. Its interaction with the Fermi surface can therefore occur at different locations, and therefore the properties can change. Okay, so I will conclude by saying now we have seen the various approaches, we have seen where one is better, where one is the other is better, and we see that regardless of the approach, ultimately it is the same material that you are discussing. So therefore to the extent that they are valid, they should predict the properties appropriately. Okay, so with this we will halt. In our next class we will look at semiconductors in detail and see what we can say about semiconductors based on the approaches we have taken. Okay, thank you.